Okay, now it worked. Okay. What happened there? Okay, so now you'll notice that the find equation worked, and in fact it rewrote the x and the goal with z by applying the using the smarts. Okay. Are there any questions? Yes.
So does this work the same if we have a relation instead of a property? Would we need to change the LTAC law?
So the question was, would this work as well if we have a relation or a property? And the answer to that is that that is exactly why the reason why this failed the first time was because this is a little subtle, but this pattern assumes that the hypothesis of this first assumption has exactly the form some property of the variable, right? And we initially had q is less than y, which if we expanded this out would actually be LTQY, right? And now it's going to fail. Why is it going to fail? Well, LT, I guess it's LE, but LEQY doesn't match something applied to Q, right? It has this Y on the end. And so by switching it to Y is less than Q, oh, but now yeah. Now everything pattern matches and it works okay. So maybe this also hints as well, this is a powerful tactic, you can imagine it might be a little bit tricky to debug. There is actually a way to get around this, but I'm not going to show that now because I'm delving into more LTAC black magic than I probably should in an intensive introductory course. Yeah, question? Oh yeah?
It was quite easy because we already directly had P of x as a hypothesis. But let's imagine a situation where P of x is provable but not directly available.
Mm-hmm.
And you could imagine this tactic with additional parameters. It would be a tactic to try to prove this P of x.
Mm-hmm.
But then, what would we do? We would rewrite H1 and then call the tactic try to prove this hypothesis Px, but we don't know if the tactic we got a parameter will change the state to an unprovable state. So we would like to see, well, if that works, great. If not, please backtrack so that we don't break the state of the proof.
Yes, okay. So there was a long question, and I will restate it as follows. There are many different ways to accomplish something using LTAC, right? And there's a different, more general approach that was suggested, but where we actually don't assume we have this H2 in hand, and instead we try and rewrite, and then we try and discharge the subgoal that gets generated with some more automation, right? But the issue here is that if we tried to do it with auto, for example, the rewrite might succeed, and then auto is not going to fail. And so what's going to be the result of running this tactic? Well, we're going to get into some intermediate state where we've rewritten, and we might have some subgoal that isn't provable. Like this tactic is somehow taking us down the wrong branch. And the question was, is there some way to augment our tactics in such a way that we will that we will automatically backtrack out of them if there's a problem? Is that accurate?
Exactly.
Okay. And the answer is yes, there is a tactical that allows us to precisely do just that. So again, this is one of the reasons auto is so nicely, because auto is not going to get you into an intermediate sort of gross goal state. It solves the goal or it doesn't. And it's clear that it can do no harm. In that sense, this tactic could do some harm. So here is, let's see if I can phrase it this way. Let's see, we're going to rewrite, and then we'll try auto. oh, now I get this. Okay, so okay, I'm debugging this on the fly. So the short answer to this question is that there is a tactical called, there are two ways you can do this. There's a tactical called solve, okay? And solve will either, here's how solve works. It applies the tactic inside here to the goal. If it solves it completely, it's done. If it doesn't, it fails, and it'll signal an error. It says no applicable tactic. Why is that useful? Well, as an example, if we tried to solve this goal with auto and it didn't work, now this is a way to make auto fail, right? To somehow signal the fact that auto was unsuccessful. And if you can imagine when you're building up this proof automation and you have these proof trees, sometimes it's useful to signal failure and back out and then try something else instead. And this is very useful for doing that. Another way we could do that is using the fail tactic, which I don't know if you've seen before. So what does fail do? Well, fail always fails, as you might expect. Why is that ever useful? Well, imagine this. The semantics of the semicolon are apply what follows, what the tactic after it, to every sub-goal that gets generated, okay? And in the case that the tactic on the left-hand side of the semicolon completely solves the goal, the stuff on the right-hand side never gets invoked, right? So if auto solved this goal, we would not, fail would never be called. And so this would be another way of signaling that the tactic signal completed successfully. Either it solves the goal, in which case we're done, or it doesn't solve the goal, in which case we throw an error. So those are the two answers to that question. Was that was helpful? Okay. Now, as you, I think as people may be absorbing, as part of this lecture and this discussion, there's a lot of sort of nifty, cool automation things that you can do in coq, and it can be a little bit of a black hole, and there are a lot of different ways to skin a cat. And so there are a number of different, one of the best ways to get a handle on this is to play with it yourself, but there is a subsequent chapter in Software Foundations in part 2, Logical Foundations of Programming Languages. It's volume 2. There's a chapter called Use Auto, which has more details on various parts of automation and how to use the auto tactic. And you might also want to check out Certified Programming with Dependent Types, which is another ebook that's available online that goes into more detail about proof automation. And then finally, you can always just check the coq reference manual, which has some good information about how these tactics work as well. Okay. This lecture is just to give you a sense of what is possible, not everything that is possible. Okay. Right, so again, just to step it back up one level, we've got this proof automated down to a single line, a one-liner, even though it's not one line, that's okay. Now, here's the payoff, hopefully. If we changed our definitions, and in particular, if we changed the definition of our language, we extended it with some new construct, the hope and the promise is that this automation will adapt to this updated statement in a reasonable way. So we don't have to completely recreate the proof from scratch. It should, in a perfect world, just still work. Okay? So what have we added? We've added this repeat construct, which is just like while, except it checks the guard after running the body of the loop once. And the loop repeats if the guard is false. Right. So the intuition here is that, do we give the semantics here? Okay, and here's the notation, and here's the evaluation rules. The intuition here is actually hinted at by the statement describing repeat. You see it says repeat behaves like while, just like while. And so in some sense, this new command should be, the proof obligations that come up as a result of doing for the cases associated with this command should be similar. They should be like while because it's similar semantically. So ideally, the automation should also adapt to handle that nicely because it should use a similar pattern of reasoning. Okay, so let's see if that works in practice. Does anyone want to guess if it works in practice? I've already sort of shown that. Is it going to work? Yeah. I love the optimism. Well, it... All right, that's fine. Oh, shoot. No, I need to actually patch up. Fine equation here. Yeah, can I just... Yep. Okay, okay, good. Back and better than ever. So it actually did not work because I messed with the tactics. That is also a danger that can happen when you mess with your LPAC. It can cause proof of strength. Okay, so the hope was that this exact same piece of LPAC would just solve the goal completely. And we wouldn't have to do anything after changing these definitions. And obviously, that did not happen. Shucks. And why did it not happen? Well, we can step through the goals and see what the issue was. So here, well, we're just going to blindly apply this fine rewrite inf tactic because we note we have an assumption of x equals true, and then we have another assumption x equals false. And we have a tactic for that, so we'll use that. But why didn't find rewrite inf find that? And let's look at the other case. Well, it's the exact same story. H right there in the middle, and then H5 down at the bottom have this something equals true, something equals false pattern. So why didn't this work? Okay. Well, it's hard to tell just on the face of it. So the trick is we'll just look at it. Well, I'll give you the answer. So the answer is that now find equation and find rewrite inf were in the wrong order. And if we just swap their order, now it magically works. Okay, which is sort of an unsatisfying maybe answer here. But why is that an unsatisfying answer? Well, so the right way to do this, and how you normally do this, is you're like, okay, this should work, but I'd like to debug my tactic. And it's a little bit hard to debug the tactic as it stands right now for precisely the reason that was suggested earlier. So this is going to succeed, and in fact, it's going to manipulate the sub-goal that was generated for our two new cases. It's going to transform it. So it's going to, what we see when we hit these cases is actually going to be different than the proof state that we would have gotten right at the beginning of these intros. Okay, because we're going to do the intros, and then we're going to apply these tactics we have in hand, and then we're going to call auto and is going to try and solve it. So what we see in the sub-case is what has happened after all of these have applied. So one better way to do this is to use our try tactic. And in particular, what do we want to do? So we're going to write a proof script that says, try and completely solve the goal with all the automation we had in hand before. If it doesn't solve it, this is going to have a no-op, it's going to fail, and that's why we put it in the try loop. So this is going to either solve the goal completely, the goals that were generated by this induction tactic invocation, or it's going to leave the proof state unchanged. And this is convenient for debugging purposes, right? So, okay, now we are in the state that follows immediately after this induction step, and we have a little bit better handle on how to solve this, how to try and patch up our tactic, okay? So here, what do? Well, we can copy and paste and try and figure out what went terribly wrong. And once we do that, once we're stepping through the goal, once we're stepping through the proofs, we can well, we can walk through the proof steps hand by hand, and we'll see exactly where the error occurred. And of course, it occurred when we tried to, when we put these in the wrong order. So as we're stepping through this proof, we'll note, aha, if I just swap these two things, then it would have worked okay. And so we'll think to ourselves, okay, maybe we'll do that, and we'll, sure. We'll, like, okay, well, let's try that. See if that completely solves the goal. It does, so hooray. And then we'll say, okay, well, I'll try that on the next one too. And it works, and we're done. And we'll say, okay, well, I'll just try and do that at the very top. And indeed, that works. And then we're like, well, since that solved everything, I have my repaired proof. Okay, so it's beautiful, right? We've got it down to a one-liner again. I think that process hopefully hinted at something to you. It's that when you see I think Andrew said this yesterday, and maybe other lecturers have said it too. When you see the proof script in an existing file, that proof script is the result maybe of someone noticing that their tactic went wrong, and then going through this process, and then cleaning it up to make sure it works. So what is the take-home message there? The take-home message is that proof engineering can be a little bit more tricky. There are artifacts and work that were associated with crafting a nice single-line proof script that you may not be able to see just by looking at the text of the proof script itself. It might have involved some more work. And so you shouldn't be discouraged if your automation doesn't just work out of the box. I guess keep trying. And maybe the higher order bit here is as well. Now we have this piece of automation should have worked on the original goal. So hopefully we've built up an even more adaptable proof here that could be applied in other situations as well. So if we wanted to change our language definition again, it should also work. It'll work better now that we've spent a little bit more time thinking about more general usage proof states you could arrive in. Are there any questions? Yeah, quick.
Is there any sense of putting in a comment when you have something highly engineered like that? Like you would in an algorithm that's
Yes.
highly optimized. A good engineer might put a good
Oh.
comment to help other people who come to it.
Oh, yeah, for sure. I would say that certainly I'll defer to Leonard on this, but if you look at the VST, I imagine the automation and the tactics are very well documented, right?
Oh, brilliant.
Yeah, I mean, it's probably the best documentation you've ever seen. But no. When people build reusable automation and libraries, they try and do a good job. I try and do a good job. It's not perfect, but yeah. There is I think there's a recognition among the community that good proof engineering depends on the same principles as good software engineering, and part of that is documentation with comments and good naming conventions and clean code and all that. So back, yeah, yep.
So related to this question, the problem with the comment is that it's just text and checked by the programming environment when compared to some language feature. And I think I have a specific example in mind now. Meaning when we make either induction or case analysis, then we can have a lot of cases, and maybe some tactic will solve half of them or most of them, but then there are a few remaining, and we decide, okay, they are way more complicated, they are different, let's just prove them manually, but there is no way to identify which of the cases it was our, except, well, we just step into it and look at the state right. But if compared with Isabel, there I saw it's possible to make a case analysis, apply some tactics, and then to part of the syntax. Well, now those 2 or 3 cases are syntactically checked so that it corresponds to the constructor.
Okay. Yeah, so I think can I restate the question as, or the comment as, it can be very hard to recover the intermediate proof states just by looking at a proof script. Is that safe? And I think that is a fair concern or criticism of this approach to proof automation or building proofs interactively. There